Hello, this is going to be my video about free fall. And let's see. Okay, so free fall occurs when an object is moving only under the influence of gravity and nothing else. This means that we ignore air friction, air resistance, and everything that keeps paratroopers alive, paper airplanes in the air, parachutes working, and the things that make styrofoam balls fall slowly but bowling balls fall quickly in real life. This one isn't actually free fall because notice here, right? It starts off moving really slowly and then it speeds up. At the end it's going real quick, but this person is moving at a constant speed down. This one is actually not free fall. It's just sort of an example of something falling, but it doesn't count because it's not accelerating. So it turns out gravity accelerates everything at the exact same rate no matter how heavy it is. The only reason things seem to fall at different rates is because of air resistance. Get rid of the air resistance and they all fall the same. So heavy things seem to fall faster, not because gravity actually pulls them more, but because heavy things can cut through the air better. And here's video proof, if you don't believe me. It might be difficult to see, but when they put a man on the moon, they had him bring a feather and a hammer with him. And then on the moon, he dropped the feather and the hammer. So in this hand, maybe you see over here, there's a feather, here there's a hammer. Look at where it starts and where it ends. Boom. The feather and the hammer will hit the ground at the same time. Because on the moon, the air resistance is almost negligible. It's pretty much none of it. So when there's no air resistance, they fall and land at the same time. So don't memorize it, but gravity accelerates everything at about negative 9.8 meters per second squared. Negative because it's normally down, 9.8 meters per second squared because that's the average acceleration that gravity exerts on Earth. You know, on a mountain it's actually less, and in a valley it's actually more, but to a very small degree. So this means that unless air friction slows it down, everything that falls gets 9.8 meters per second faster or slower every second, depending on if it's going with or against gravity. It's about 22 miles per hour. It's pretty fast. Things that are falling down speed up, like that, and then things that are going up slow down until they reach zero. So notice that this ball, which goes down, starts off moving slowly and ends up moving very quickly. But these balls, they start off going very quickly in the first second, they move up less in the second second, less in the third second, and then they totally stop. This is because this ball is going with gravity. That's gravity. The ball that's going with gravity speeds up. But this yellow one, at least on the way up, is going against gravity. So it slows down. So notice something. If you toss an object with a positive velocity, meaning that it is going up, that's what the positive means, it starts going up, as you would expect, then it slows and stops. At a certain point, it stops moving up and starts moving down. And that's always going to be at the peak of its fall. So here and here, they stop moving up and then they start moving down, which means that they go from a positive to a negative velocity. So the velocity is actually zero when the ball is at the highest part of the motion. This is what a position versus time graph would look like something under the influence of free fall. If it started from rest, which means you just drop it, it would look kind of like this. But if you tossed it up, it would look like this. So this is going to be the position versus time graph for that ball. I'll show you again. Here. Starts off with a lot of positive distance, then a little bit, less, less, none. After that, it starts moving a negative amount of distance per second. So it looks like this, going up at the top, and then when it's going down. So this one, if I drew it correctly, would just look like the second half of this graph. But I didn't, it's a little bit too slanted here. If it starts from rest, then it starts with zero velocity and then it falls. So actually, if I was a better artist, this right here would look like the second half of this. So something falling down, this is what not a position versus time, I'm an idiot. Oop, nope. This would be a velocity versus time. So, if you just drop it, then it will start with zero velocity, not moving, and get faster and faster and faster downward, meaning the velocity will become a more and more negative value as you go along. And you remember that the acceleration is the slope of a velocity versus time graph, so this has a constant velocity. This is a constant slope. So the rise over run, the slope is gravity. Over here, this is what happens if you start it tossing it up, right? So you start tossing it up, and then it slows down, stops, goes down, goes down, goes down. So if you start with a positive velocity, it gets slower and slower and slower until eventually it hits 0. This is at the very top. Then the velocity gets more and more negative as it starts going down. So this is when it's going up. This is when it's going down. And notice that the part where it is going down looks the same as if you just dropped it from rest, like it never went up in the first place. So this is an example of symmetry in physics, and symmetry is one of the most concepts in the entire field of physics. To really understand the world, understanding the idea of symmetry is just as important as understanding equations. So symmetry occurs when some things are the same in different parts, basically. They are the same when you do something to it. So notice that the up part and the down part look basically exactly the same. Like when it's going up, if you just froze the video right here and then played it in reverse, it would look just like it would if it was falling down. Here's another example, right? The velocity and time graph. This is the middle of this whole thing. And you notice that the up part looks like the mirror image of the down part if you flip it. Similarly, with the position versus time graph, the up part, where it's going up, looks like the mirror image of the down part. Basically, this means that this is the peak, right? 1 second before the peak, it's right here. 1 second after the peak, it's right here. This is the same position. 1 second before that, it's here, and 1 second after that, it's here. Same position. It traces out exactly the same points in the reverse order. Anyway, hopefully this was helpful.